In this section, we'll continue to look at the chemistry of liquids and solutions. Specifically, we'll look at a particular type of chemical reaction called a precipitation reaction. Precipitation reactions are a general category or class of chemical reactions that occur in aqueous solution. What all precipitation reactions have in common is that they share a general form between what their reactants and products are. The reactants in precipitation reactions are always aqueous salts. We've seen previously that this simply means salt or ions dissolved in water. For instance, aqueous sodium chloride is simply sodium ions and chloride ions dissolved in water. The other thing that all precipitation reactions have in common is that at least one of their products is a solid. This is also known as a precipitate. So another way to explain precipitation reactions is to say that they're a chemical reaction that occurs when you start out with many different species dissolved in water and you end with at least one solid. The precipitate itself, or the solid, is often basically a residue that occurs when you combine these different aqueous salts. And in fact, you might be familiar with precipitation reactions if your household water leaves a residue on your taps or shower nozzles. That residue is a precipitate that forms when aqueous salts that are naturally occurring in your drinking water come together to form a solid precipitate. Some of the salts that are involved in this reaction include things like calcium, magnesium, carbonate, and bicarbonate, although there's many others. Precipitation reactions also drive the formation of kidney stones in the human body. Many of the kidney stones that occur naturally are the result of combining calcium, which is naturally present in our bloodstream and intestinal tract, with oxalate, another complex polyatomic ion. The precipitate that forms, calcium oxalate, is more commonly known as a kidney stone. And of course that's a problem because while the salts are dissolved in the body, they can move freely. But once they form a solid precipitate, they're stuck, in this case, in the kidney and often need to be removed. Precipitation reactions also drive the formation of what are called stalactites and stalagmites, cave formations. So if you've ever had the opportunity to be in a cave where there's things hanging from the ceiling or perhaps growing up from the floor, these are formed because, again, aqueous salts that are naturally dissolved in groundwater, runoff, and rainwater come together to form a solid precipitate. So there's many different individual precipitation reactions, but they all follow this general form. You start out with some species dissolved in water, and in the end you form a solid precipitate. Because we're going to look in more detail at these reactions, let's take a second to do a quick review about some of the ways that ions can exist both as solids and in solution. All ionic compounds, we've already seen, have the form of a cation and an anion bonded together. In this case, I'm simply going to refer to them as AB, A being the cation and B being the anion. A solid ionic compound, as indicated by the S as a subscript in this case, simply means that the ions are still together. So NaCl solid would be a sodium ion and a chloride ion bonded together through an ionic bond. We've also seen that many ionic compounds have more than one of the cation or more than one of the anion. For instance, MgCl2. There has to be two chloride ions in this case because we know that as a whole the ionic compound has to be neutral. So since magnesium has a 2+ charge, each chloride only has a 1-, so magnesium chloride is actually comprised of 3 separate ions, 2 chlorides and 1 magnesium. And finally, don't forget, we also have learned about polyatomic ions. Polyatomic ions are individual ions that are comprised of more than one atom. Watch out for these when looking at ionic formulas. For instance, magnesium sulfate, which we've studied before, is comprised of a magnesium ion with a 2+ charge and a sulfate ion, which has the chemical formula SO4 with a 2- charge. We haven't memorized these polyatomic ions, so during this section you may want to take your polyatomic ion chart out to refer to. One more quick piece of this review is to remember what happens when you place certain ionic compounds into water to create an aqueous solution. When ionic compounds are placed in water, if they follow the solubility rules and dissolve, it really means that they dissociate or separate from each other. So if I have an ionic compound, AB, and I write it with the subscript AQ, meaning aqueous, I'm actually indicating that the A and the B have separated from each other. And that's important to remember because each individual ion goes its own way. That means in a compound like magnesium chloride, the one magnesium and the two individual chlorides will all go in separate directions. Keep in mind, polyatomic ions stay together. So in magnesium sulfate, the magnesium and the sulfate will separate, but the sulfate as a whole, meaning the 1 sulfur and 4 oxygens, will stay together. We learned how to use a solubility chart several sections ago to determine whether a compound will or will not dissolve. Take a moment to find your solubility chart and review how to determine whether you have a solid or an aqueous compound. Remember too, compounds that are soluble dissolve and therefore are aqueous in solution, whereas compounds that are insoluble do not dissolve and therefore will be solid. Now that we've done a little bit of review, let's look in more detail at precipitation reactions. All precipitation reactions follow the general form of having aqueous species that come together to form at least one solid precipitate. What essentially has happened is at least two of the ions that were aqueous combine together to create a new insoluble compound. How do you know when this happens? Well, we have to look at what the initial reactants are. As we already said, in all precipitation reactions, your reactants, or the species on the left side of the arrow, will be aqueous. But how do you know what's actually going to form? Well, when it comes to predicting the chemical compounds, or the actual formulas, we have to use something called the principle of double replacement. Double replacement means we're going to change which ions are associated with each other. In this case, I have two ionic compounds, AB, which is dissolved in water, or aqueous, and CD, which is also aqueous. In a precipitation reaction, what will essentially happen is the cation from one of the compounds will leave the anion it's currently bonded to, and it will react instead with the anion from the other compound. The result is your products are comprised of a new ionic compound. In this case, one compound would be AD. A is the cation, D is the anion. The other compound that would forms from the remaining ions. In this case, the cation C will react with the anion B. Remembering that we always write the cation first, this means that my other product in this reaction would be Cb, because C is a cation and B is an anion. That only goes as far as telling us, theoretically, what chemical species will occur. But it doesn't tell us anything about whether we have an aqueous compound or a solid, a precipitate. That's where you have to use your solubility chart. So what you would do is look up the chemical formulas on the solubility chart and determine which one of these was a solid. For instance, if we looked up AD, whatever compound it may be, on the solubility chart and saw that AD is actually soluble, we'd still write that it's aqueous, or write an AQ to symbolize that. In other words, A and D are still floating freely, dissolved in the solution. But if we look up CB on the solubility chart and find that it's insoluble, we have to write an S, meaning that that is now a solid. In this case, CB would be our precipitate. It's a solid that formed because those individual ions came together. Another way to think about this is it's as if you have an entire soup of all these ions mixed together. The fact that we write them together as AB and CD at the start of the reaction doesn't actually indicate what's really happening. In reality, A is separate, B is separate, C is separate, and D is separate, and they're all floating around in this sort of ionic soup. Then, from across a crowded test tube, their eyes meet. And in this case, C and B are so attracted to each other that they come together to form the precipitate. A and D, meanwhile, are left mingling around that ionic soup. Let's look at a specific example of a precipitation reaction. This is the reaction between sodium fluoride, an aqueous compound, and copper 1 chloride, another aqueous compound. Based on the chemical formulas and what we've already learned, we know that sodium fluoride is actually comprised of a sodium ion and a fluoride ion. Now technically, when we say they're aqueous, we know that they're separated from each other and floating in solution. But for ease of understanding, I'm going to put them next to each other here. The other compound is copper 1 chloride. Chloride, of course, is in group 7 and has a -1 charge. Copper, which is a transition metal, can have different charges, but in this case the fact that it's bonded to chloride means it must have a 1+ charge. Again, because copper chloride is aqueous, we would expect the copper ion and the chloride ion to be floating freely and separately from each other in the solution. But for, again, ease of understanding, I'm going to put them next to each other here. So what happens when you combine these two ionic compounds? Well, basically we look at the cations and the anions that are together, and we do a swap. We exchange which cation and which anion are associated with each other. Starting with our first compound, sodium fluoride, we take the cation from this compound, sodium, and we bond it with the anion from the second compound, chloride. When sodium and chloride come together, they make sodium chloride, the compound, with the chemical formula NaCl. We'll come back to looking at the physical state for this compound in a moment. Let's figure out instead the other compound that's going to form. As you can see, when I go to look at what ions are left, I have the cation copper 1 with the anion fluoride, which has a 1- charge. Copper and fluoride come together to make a compound called copper 1 fluoride, and the chemical formula would be CuF. Notice as we did this, all of the ionic charges are canceling each other out, so I've created neutral compounds. It's important to remember, and we'll see an example in a second, that if you can't create a neutral compound, you're going to have to adjust your equation by adding some extra balancing. We'll see that momentarily. In this case, however, I've created a compound, sodium chloride, and a second compound, copper 1 fluoride. Now let's look at the physical states. As we go to our solubility chart, and you're welcome to use either the one in your textbook or the one I've provided for you on our webpage, we see that sodium chloride is a soluble compound, and soluble compounds are actually aqueous, meaning dissolved in water. So the reality is, I didn't make a new compound, sodium chloride, because the sodium and the chloride are still floating freely in solution. When I look up copper 1 fluoride, however, I see that it's an insoluble compound, meaning a solid will form. This is our precipitate. So in this chemical reaction, we essentially had a little bit of an ionic soup. We had sodium floating freely, fluoride floating freely, copper 1 floating freely, and chloride floating freely, all in solution. Then, from across the crowded test tube, the copper sees the fluoride, metaphorically, and the copper and the fluoride come together to make a solid product. Meanwhile, the sodium chloride is still floating around in this solution. This is a classic example of a precipitation reaction because my reactants are aqueous salts, and among my products I've formed at least one solid, called the precipitate. Let's look at another example. This example will require a little bit more attention to detail so that we ensure we create correct chemical formulas for our respective ions and compounds. In this case, we're going to look at the chemical reaction between aqueous sodium chloride and aqueous lead nitrate. thinking as we did on the previous page about what actually is happening in these different compounds, we can remember that sodium chloride is really comprised of sodium ions and chloride ions. Again, in an aqueous solution, they'd be floating freely and separately from each other, but we'll show them together here just to keep things simple. Then let's look at our other compound. Our other compound is comprised of 2 different types of ions and 3 ions total. The reason for that is that I have 1 lead ion. Lead has the chemical symbol Pb. Then I have 2 NO3 ions. These are what are called nitrate ions, and they're an example of a polyatomic. How do I know what charges to put on these? Well, nitrate, being a polyatomic, is listed on all the charts of polyatomic ions in the world. And if you look up nitrate's polyatomic ion, you'll see that it always has a -1 charge. This in turn can tell us what the charge must be on that lead ion. If I have 2 nitrates which are negatively charged, that means my 1 lead ion must have a 2 positive charge. So this is actually the compound lead-2 nitrate. Now let's predict what products will form on the product side of this equation. In other words, what are the chemical formulas for the products? Even though we have a little more to consider here, keep in mind we're simply exchanging through double replacement cations and anions. In my first compound, my cation is sodium. In the second compound, my anion is nitrate. So I'm going to combine the sodium from the first compound with the nitrate from the second compound. Be warned, we have to make sure our ionic formulas make sense. Just like we learned quite a while ago, all the ionic charges have to cancel out. So as I take my sodium and bond it with nitrate, I have to recognize that sodium has a 1+ charge, nitrate has a 1- charge. So I don't need both nitrates to bond with 1 sodium. Instead, when I put these together to make a compound, I just need 1 sodium and 1 nitrate. Remember, when dealing with polyatomics, I don't need parentheses unless I have more than one of them. Now you'll notice that does leave an extra nitrate on the reactant side. We'll come back to this in a second, but that's a surefire indication that I am going to have to balance this equation to fully accommodate what's happened. After we do the sodium nitrate, let's look at what the other product that forms is. We know that the cation from my second compound is lead-2+. The anion from my first compound is chloride. Again, remembering that ionic compounds have to be neutral, meaning the charges have to cancel each other out, I don't have enough chloride to bond with the lead as it is. In other words, my lead is a 2+, my chloride's a 1-. Essentially that means I'm going to need 2 chlorides. And this is where you can start to see how the balancing is going to come into play. In order for the lead nitrate to react with the sodium chloride, I actually need 2 sodium chlorides. The reason is, for each 1 lead-2+, I'm going to need to bond it with 2 chlorides. That's going to create my second chemical compound, or my second product, lead chloride, or lead-2 chloride if we're being precise. Notice that this leaves on my reactant side 1 sodium and 1 nitrate, which perfectly cancel each other out. In other words, my products of this reaction aren't just 1 molecule of sodium nitrate and 1 molecule of lead chloride. It's 2 molecules of sodium nitrate for every 1 molecule of lead chloride. I know that's a lot of different information to remember, but don't be afraid to pause the video, go back and rewind it, and notice how the different subscripts and the different coefficients or balancing numbers have allowed this equation to actually make sense. In the end, I really had 2 molecules of sodium chloride reacting with 1 molecule of lead nitrate. Then my products are 2 molecules of sodium nitrate and 1 molecule of lead chloride. Finally, I have to decide what precipitate formed. When I go to the solubility chart and look up each of these products, I see that sodium nitrate is actually a soluble compound. so I'll write that it's aqueous. In other words, all those two sodiums and two nitrates are doing is still floating freely in solution. The lead chloride, on the other hand, is insoluble, so I'll write an S for solid. In fact, this lead chloride would form our precipitate. So when I combine 2 molecules of sodium chloride and 1 molecule of lead nitrate, I still have 2 molecules of sodium and 2 molecules of nitrate floating freely, but I've made 1 molecule of lead chloride, a precipitate. In each of these previous examples, our final chemical equation showing reactants and products was actually what's called a molecular equation. And the reason it gets that designation is that we wrote all of the compounds together, regardless of whether they were solid or aqueous. For instance, in the reaction between sodium chloride and lead nitrate, we used AQ in compounds like sodium chloride to indicate that they were dissolved in water. We know ionic compounds, when dissolved in water, actually dissociate. So there's not actually a molecule of sodium chloride. There's separate ions of sodium and then separate from chloride. Still, writing it together can be very convenient, so we call this a molecular equation because it shows all the compounds written together, even when in reality some of them may have dissociated. What's a little bit more honest, but also much more time-consuming, is to write what's called an ionic equation. An ionic equation, like the name implies, shows each individual ion that's present. You can take a molecular equation and just based on what we understand about aqueous salts, turn it into an ionic equation. I'll show you how. For instance, in our molecular equation on the top, we have 2 molecules of sodium chloride. Because we know sodium chloride is an aqueous ionic compound, as indicated by the AQ and what we've learned previously, we know that this really means you have sodium ions and chloride ions that are separated from each other. So for those 2 molecules of sodium chloride, I actually have 2 sodium ions and 2 chloride ions that are separate. When we look at the lead nitrate, we can arrive at the same conclusion. The lead nitrate is an aqueous ionic compound, so we know, even though it's written in the molecular equation altogether, what it actually tells us is that I have 1 lead 2 plus ion and 2 nitrate ions that have separated from each other. Same thing on my product side. I have 2 sodium nitrate compounds. Well, those sodium nitrates are actually comprised of sodium ions and nitrate ions. Because there's 2 of them, I have twice as many, 2 sodiums and 2 nitrates. In fact, the only compound in the molecular equation that stays the same in the ionic equation is the precipitate, because it's a solid. So the lead chloride that resulted is truly lead and chloride ions bonded together. We can write that just as is. Now looking at this, it is a little bit more honest to write an ionic equation because it tells us we didn't really have molecules of sodium chloride and lead nitrate reacting with each other. Instead, we had a soup of sodium ions, chloride ions, lead ions, and nitrate ions. And when they came together, all that actually changed is that we made lead chloride. The sodium and nitrate were still floating freely in solution. For this reason, what most chemists really care about is what's called the net ionic equation. It's an ionic equation where we've removed everything that's a spectator. We've seen the term spectator before. We know it just means a compound or an ion or any chemical species that doesn't do anything during a reaction. In this case, an example of a spectator ion would be my 2 sodium plus ions. If I look, each side of the equation has 2 sodium plus ions. So sodium simply served as a spectator. Nothing more complex happened. Another example of a spectator ion in this reaction are the 2 nitrate ions. They appear identically on the left side of the arrow in the reactants and the right side of the arrow in the products. If I remove all these spectator ions, what I have left are 2 chloride ions and 1 lead 2 plus ion, which reacted with each other to create, on the product side, PbCl2. In other words, the net ionic equation for this reaction says take 2 chloride ions, 1 lead 2 plus ion, and you can make the solid lead chloride. If you can see where the net ionic equation comes from, you don't need to write a full ionic equation to get there. And in fact, most chemists are perfectly happy with you writing the net ionic equation. Here's one of the reasons the net ionic equation is valuable. If you wanted to make lead chloride, or find out if it would actually form, this tells us that all we need are 2 chloride ions and 1 lead 2 plus ion. In fact, I didn't need sodium chloride and lead nitrate to do this reaction. I needed any compound that had chloride ions and any compound that had lead ions. Because whether I use sodium chloride, potassium chloride, lithium chloride, or another compound, the sodium or potassium or lithium would simply act as a spectator. Here's a good practice to do for precipitation reactions. Complete the following precipitation reaction with correct chemical formulas, physical states, and balancing. Then write the net ionic equation for the completed reaction. In other words, determine what products form, which is solid and which is aqueous, and ensure your final reaction is balanced. Then write the net ionic equation. Remember that you can write the complete ionic if you find it to be helpful, but most scientists care most about the net ionic. Pause the video and restart it when you're ready to check your work. There isn't really a trick to getting these reactions right. It's mostly just remembering a bunch of different rules that we've learned previously. I'll start by writing the correct answer, and then we'll talk about how we got it. You could skip the explanation if you feel comfortable with it. One of the products of this reaction is magnesium nitrate, which has the chemical formula MgNO3 in parentheses because it's polyatomic with a 2. This is an aqueous compound because if we look it up in the solubility chart, it is soluble in water. My other compound, or my other product in this reaction, was chromium 3 chloride, CrCl3. And when I look that up on the solubility chart, I see that it's insoluble. In other words, it forms a solid precipitate. Let's look at how we got this. We already know we're going to take the cation from the first compound and the anion from the second compound. When I do that, however, I have to take into account what charges I have. Magnesium has a 2 plus charge, nitrate, a polyatomic. I can look that up on a polyatomic chart and learn that it has a 1 minus charge. Following the rules that we learned quite a while ago about forming ionic compounds, I have to make my 1 minus charge cancel my 2 plus. That's why I needed 2 nitrates to complete this compound. My other compound was chromium and chloride. Again, I have to follow the rules about making charges cancel out to make an ionic compound. We already know that chloride has a 1 minus charge. That's why we needed 2 of them initially to cancel out the 2 plus charge on the magnesium. Chromium has a 3 plus charge in this compound, and I can tell that because it's bonded to 3 nitrates, or 3 -1 charges. By looking at this, I can see that I need, for every 1 chromium, I'm going to need to have 3 of these chlorides. That's how I decided to write CrCl3 as my final product. Don't get confused by all the different subscripts that are involved, because when I look at this, my subscripts sometimes are part of polyatomic ions and sometimes are simply giving information about how many ions we need of each particular ion to cancel out the charges. Now let's look at the net ionic equation. The key to writing a net ionic equation quickly is simply to identify your precipitate, in this case CrCl3, and then to figure out what you needed to make that compound. So the product that I'll write in my net ionic equation is CrCl3, solid. Well, what did I need to make the CrCl3? I needed 1 chromium, which has a 3 plus charge and was aqueous, and I need 3 chlorides. Each one has a 1 minus charge, and they're aqueous. So my net ionic equation is simply Cr3 plus aqueous plus 3Cl minus aqueous, which forms CrCl3 solid, a precipitate.